Good morning, everyone. Welcome back to a new talk for our series Next Friday Talk. Today here we have Francesco Peverelli as speaker, PhD at the end of his journey here at NextLab, who's going to present us one of his most recent jobs that has been performed in collaboration with MIT also. So thank you, Francesco, for joining us.
Thank you, Laura, for the kind introduction. And yeah, without further ado, I'm going to share my screen and we can start the presentation. Okay, so hello again, everyone. So as Laura was saying, today I'll be talking about one of the works I've been recently developing, which is called MARCH, which is a multi-staging array compiler for high-level synthesis that has been developed in collaboration with the commit group at MIT. So I want to start by giving a brief context on FPGAs and high-level synthesis and sort of try to explain to you why these work, where they come from, and where does the need for something like this come from in the first place. So basically, FPGAs are configurable hardware that can be programmed via a bitstream that realizes hardware functions. And the bitstream is obtained through a synthesis process, which uses as source some RTL code, and then maps this to the available hardware resources on the FPGAs, allowing it to be programmed in whatever hardware function we need. High-level synthesis comes trying to raise the level of abstraction of this process because it wants to transform imperative high-level language code, so for example, C++-based code, to RTL automatically. So this is a very good idea, but the problem is that, of course, it's a very complex task because imperative code is very different from RTL code, and HLS tools need to do a lot of optimization and transformation to go from C++ to RTL. So the problem is that these tools, being so complex, perform a lot of transformation which sort of act as black boxes, where it's sort of hard to understand a priori what's going to happen once you take your C code and give it to the tool. And to ameliorate this, there is a lot of code that needs to be written in sort of a canonical form that somewhat restricts the freedom of the developer, but also ensures that the result is what we want. In addition to this, sometimes the developer needs to add some specific pragmas to basically tell the HLS tool that the program has some properties that are not readily apparent or even not able to be inferred at a compiler level. So in this example, we can see that the code has some pragmas that say that the buffers in the if condition have some dependencies, inter-iteration dependencies that are false. So there will never be a dependency between these statements. And this allows, of course, the HLS tool to perform further optimization, but if these conditions not hold in practice, then the code will be wrong. And the programmer needs to understand this and basically tell the HLS tool what to do. So I'm just going to go through a brief example of a vector addition in HLS to show you how even a very simple code can become very complex very quickly. So this code, as it's written in this slide, does not compile because for first thing, we need to specify some AXI interfaces for the kernel, which means how the programmable logic of the FPGA will interface with the rest of the outside world. So here we can see that we have added this fragment to specify the AXI interface for the kernel. So now this code works, but it's very inefficient because what we do is we basically read data one by one from the DR, and we are not fully leveraging the capabilities of our AXI master interfaces. So in this third slide, we have a fairly optimized version for the vector addition, where what we do is we have three pipelines, basically that read the A vector in a burst fashion, the A vector in a burst fashion, and then perform the addition. Moreover, we've also packed the elements of the vector so that we can better leverage the DDR bandwidth, and then we also perform a reduction in parallel between packs. So as you can see, it's a more optimized version of the code, but it looks almost nothing like our original code. And this is just to show you that we have a lot of boilerplate code and complexity that rapidly increases in one of our optimized HLS. So can we adopt a compiler-based approach to generate this sort of code? Well, people have been doing this for a while, and in state of the art, we have several tools that attempt this very thing. The all these tools work somewhat, but they have their own set of issues. And in particular, a lot of tools do not take into account global data flow optimizations. And also, they are mostly based on MLIR or have some other input language such as Python or custom languages. In addition, what we want to offer that is not present in state of the art is the fact that we can, with March, we want to be able to integrate hand optimized components if the developer needs a particular optimization implemented in a hand-written way. Whereas all these compiler-based approaches do not allow this because they have their own input language, and if you cannot express what you want in the input language, then you have no way of implementing it. Moreover, we want to also introduce a more programmatic way of parameterizing your kernels, which means you want to stay within the boundaries of C++, but also be able to add all the parameterization freedom that you need to generate different sort of kernels according to, for example, the input data you have. So in order to do this, we want to apply a multi-staging approach to accelerator design languages. What does this mean? Well, we can think of the rationale for staging into 3 steps. So basically, staging means that you have a program, and you compile this program, and the result of the compilation is another program. So basically, you compile the program in steps. And at each step, you optimize some part of the program that is known and can be optimized away. So with staging, we can allow this flexible parameterization on the first stage, and then ensure that the code is written in a canonical way that we want in the as input to the HLS tool. We can remove runtime conditions, so you can have simpler hardware generation and better performance. And also, it has been shown that multi-staging can be used to develop DSLs in a more agile way, writing less compiled code than traditional LLVM/MLIR-based approaches. So, in the way in which we do this is we have a program source code and then a staging compiler that uses some additional staging input to create a stage program. So we use Buildit to perform staging, and Buildit is a C++-based staging framework that uses templates and template types to do staging. So what Buildit does, it creates what is called dynamic variables and static variables, where static variables in the code are optimized away in the staging process, so have a particular value for each staging set, and so they get simplified away. In this example, we have a power function where the exponent is a variable, and we have the corresponding implementation of power 3, which is the optimized function for the case where exponent is 3. And so in this case, Buildit optimized away the control flow that was written to the fact that the exponent was variable in the second stage. And so we have the optimized code, specialized code for exponent equals to 3. In this case, the additional staging input we talked about are the static variables. So what is March and how does it work in broad strokes? So what we want to do is we want to create a compiler that takes some higher level array language and outputs HLS C++ in an optimized fashion. So we can divide the framework into 3 main steps. The first step is we have defined a DSL embedded in C++, which we'll see in a moment, the array-based language. We extract the AST of this array-based language, and this AST extraction also performs the first staging mechanism. So we have some static variables in the code that have been optimized away, and in the second stage we have an optimized AST of our high-level language. Then we have a problem, which is that we need to perform, for example, global optimization on the whole code. But staging is inherently a sequential process. So in staging, you go through the code and basically you simplify it and optimize it according to the value of static variables. But what we need is we need to have first a look at the whole program and then decide what optimization to apply and how they interact with each other, and then use staging to implement. So what we do is we take the AST and we analyze it in a more traditional compiler way. So we create a photo graph, we perform analysis on the second stage AST, and then, as it's been shown to be an effective strategy, we use a scheduling code language to define optimization. So what happens is that we have performed some analysis on the code, we have parsed the scheduling commands that the user has given us, and we use those to generate the optimized code. And the way we should do it is that the second stage is also a stage program using Buildit. So the visitor, the one that produces the code, is staged so that there are static variables within itself that depend on the results of analysis. So that depending on the analysis results, you can generate different types of code. Then we have basically an optimized scheduled C++ code for which we again extract the AST and then perform some cleanup stages, some more traditional compiler-based optimization passes, so that's code elimination, and so on. And then we generate the final HLS by using basically an HLS code generator, which outputs the code in the form that the tool requires. So looking at the first stage, I just want to show you a brief example of the AMD language. So we have these array structures, so directing var array AB res, for example, that are arrays for which you can set a size that can be either a static size or dynamic size. And then we have indexes. So indexes define the iteration space for arrays. So in this case, you can say that index I that for which you set iteration space from 0 to size with a stride of 1. So then you basically just write statements involving the arrays without loops or control flow. So you just say for each point in the iteration space, perform some operation. So A of I equals I is for all the points in the iteration space, then A of I becomes the iteration index. And so on and so forth with these other small examples. So basically, just to recap, we have array objects that define what to iterate on. We have indexes that define the iteration space, and then we have assignment statements that define the computation that is carried out at each loop nest. So what this code becomes is the corresponding loops that you have defined with your arrays in iteration. In this case, you have 3 for loops that each do the whatever statement was in the original array language. Of course, you can do a few things with this. You can do reductions. So if you have variables for aij on the left hand side and b of I on the right hand side, you have double nested loop and you reduce the amount of the vectors. Then you can do indirection, so you can also use an array to index another array, which creates an iteration space which is based on the values of that array. And in this way, you can do, for example, SPMB and all the sort of histogram. And whenever you need interaction, you can use this feature of the language. Then, since the first stage is also a staging portion of the code, what you can do is you can use static variables to basically decide at runtime which sort of portion of the code to produce. In this case, for example, we have a condition that decides whether we do segment 1 or segment 2 in the second stage. And you can do this also by using static variable splitting loops, which means that you basically produce a finite set of statements for each value of I that gets repeated sequentially in the second stage code. You can also mix in dynamic control flow if you use dynamic variables or control flow, and this will work seamlessly with your array statements. So having a look at the scheduling transformation, which are the core part of the implementation of this compiler. So as we said before, the basic idea is that the second stage generator itself is a multi-stage build function. And so we have carried out double analysis, and we can do scheduling based on the results. So this is a brief overview of the lower level APIs for scheduling. So you can say a lot of different things to specify optimizations on the code. So select the memory storage type, select where these temporary storage is to be placed in the nesting level statement. You can select where you read data, and then you can do a bunch of other loop-based optimizations such as fusion, such as splitting, and then we also introduce some more HLS-specific optimizations such as array packing, which allows you to change the data type of your elements in the array for wider types, for example, for parallelization purposes. So I'm going to give you a few examples. Here we have the use of the read_as command, where we have a vector and we say, so read this vector as a string, and we also give a particular implementation binding to the vector so that it's implemented as a VRAM on the FPGA. And we can see that the resulting code has a load loop, which basically writes a string with the elements of the vector, and then it has a second loop where the string is read and is used in the actual computation. This is useful because it allows you to express, for example, data flow pipelines in HLS by using this sort of load store programming paradigm. Then we also have load at and read at commands, which once you have decided what type of storage you want for your element, allow you to decide exactly where you want to load temporary and where you want to read. So load at basically defines also the actual size of your temporary. So if you have a two-dimensional iterative space and you load at in the first dimension, this means that you are, for example, you are only storing the rows of a matrix and not the whole matrix of temporary. And read that basically tells you when you want to actually read the temporary storage to then do the computation. You can see that in order to keep things consistent, if you basically load things into a temporary, then you modify your vector, then you will automatically generate a store loop to basically make the, let's say, global memory and consistent with the computation you have done. So in addition to this, we have load store with modifiers. So these basically allow you to decide how you want to carry out the computation, and for the most part, translate into pragmas on HLS loops. So for example, you can specify if you want a loop to be unrolled, if you want a loop to be a pipeline, and so on and so forth. And you can place it either at the loading of data, storing of data, or at the part of the data. Then we have fusion, which allows you to fuse statements, can be useful if you want to add some statements implemented as a single pipeline. So you don't want multiple loops. Then you can do loop interchange by using the schedule iteration API. It allows you to order the iteration order of your loops in a statement. Index splitting basically means that you have an index and you take that index and you decide to split the iteration space by a factor. So this generates now two loops, and it also transforms the index to reflect the fact that you have now basically a linearized two-dimensional iteration space that you are iterating through. And then finally, data packing is what allows you to change the data type width. And what you do is you have an array and specify packing factor. This will change the data type of your array using, for example, arbitrary integers from HLS. And you will also change your indexes to reflect the packing. So in theory, this expression can become very complex if you do packing that does not agree well with the dimension of the arrays and the dimension space. But if you follow a few rule of thumb rules with the agreeing of the iteration space and the packing factors, you can simplify this expression to have what you would expect from packing an array with a factor that makes sense. So then it becomes very optimized code. So since these scheduling APIs were quite cumbersome to use if you have to use a lot of schedules, what we did is to also add some composable schedule APIs. So what these do basically is they save the schedule and allow you to construct it basically step by step and store it in an object, and then to apply it whenever you want to different objects. So basically, you have the equivalent of the command we've seen before, but in this case, they just save a structure of schedules, for example, where you want to store the array, what type of memory, if you want to do the shaping, and so on and so forth, and then allow you to apply it either to an access or to an array object. Similarly, we have the same thing for loop schedules, so that you can decide, for example, that you want to both pipeline a loop at some iteration level, and then use dataflow at another iteration level, and also fuse the statements together. So you can just chain these commands into the loop schedule, and then you can apply it to whatever loop you need to apply it to, and so that usually multiple times. In addition to basically differentiate, do hardware-software partitioning, understand which functions in your code you want to be accelerated, and which function you want to run on the host, we have APIs that allow you to basically designate some portion of code as you run your hardware, and also APIs that allow you to define that you want a hardware sub-process that can be a normal sub-process or a critical sub-process, for example. These are basically C++ lambdas, in which you enclose your code and allow you to basically outline the code into a kernel or outline the code into another function within your directory. So just to show you a brief example March in action. So this is a simple implementation of a CO SPMB pipeline. So what we do first and foremost is we declare some arrays that basically implement our CO encoding, and then we set their dynamic sizes. We use the stop function lambda to designate that the portion of the code that follows is indeed a kernel function. Then we define the iteration space, which depends on the number of zeros. And also then we basically implement the actual state. For example, y of rows of non-zero is accumulates values of non-zero times x of columns of non-zero. So this results in a fairly unoptimized implementation, of course, but that is a working implementation. We have the director phrasing, and then we have the loop that depends on the indices and that performs this implementation. So what we want to do now is we want to add a custom schedule. So this is a fairly different way of doing the same thing that you could do with a composable schedule, basically. In this case, what we did was just define a lambda with a few scheduling commands in it, and then we will use the lambda and apply it to different arrays. So basically what we do is say we want to read the A method string with a particular depth and implement it with a particular memory. Then we want to load it at the outermost iteration index, called abstract index root. And then we also want to schedule the computation of the Python. So what this does is create fairly more complicated code where you first write the method into a stream and then you read it as a pipeline, and you have a data flow kernel, which is a lot more optimized than before. Then, in addition, what we could do is we could want to split the computation into three different processes. One that reads the vector, one that computes the SPMB, and one that writes the vector back, the Y vector. So this can be done by adding a few more temporary arrays and also splitting the top function into sub-functions. So you can see here that we have a Y local and X local sub-vectors. We use a first hardware process to read the input into the local vectors. Then we have a compute process that performs the actual computation. And then we have a store process that takes the local result and writes it back to the DDR. So what it means is that we end up with a pipeline that looks somewhat like this in a very high-level schema. So you read the extract from the DDR, you read the rows, columns, and values, you compute SPMB, and you store the Y vector in a local memory, and then you write it back to the DDR. So this was just to give you an idea of how we can use the framework. So what we did was we want to compare March with our state-of-the-art ADLs. So what we did, we compared the performance of March against a few other tools on the polybench benchmarks. So the polybench benchmarks are a typical algebra, basically a collection of algebraic kernels that are typically used to assess the performance of these tools. We run all these experiments on byte HLS 33.1, and we target another U250 board. All the kernels are synthesized at 300 megahertz, and basically the results we obtain are shown in this slide. So we can see that in terms of latency, there is basically only one tool which is competitive with March, which is Allo. And we have a geometric latency improvement on 1.8, it's 1.06 times with respect to Allo, which is not striking, but it's expected because what we did in this test is basically implement the same sort of schedules and optimization that Allo used in terms of what optimization we want to perform, and the difference is only driven by some differences in how the code is actually produced, so what the code looks like, how we divide functions, and so on and so forth. Basically, the goal was to show that even a multi-staging approach, as opposed to traditional MLIR-based approach, can perform the same optimizations and can deliver the same kind of performance. You also see in the resource utilization comparison that we have a lot of similarity, but that we also can see different types of trade-offs. So in some particular cases, for example, the 300 case, we do a lot better with March than Allo, because basically we have a way of writing the code that doesn't make the HLS tool use as much local storage. But for the most part, the results show that the performance are comparable with some trade-offs between use of resources, for example, trading loop utilization, for the speed utilization, and so on. All of these can be actually controlled by adding some more scaling, but we want to show basically the code in the way that it's produced with the minimal amount of optimization required and using as much high-level expressions as possible. So in conclusion, we see that there's comparable utilization with some trade-offs in specific cases. So moving on from the poly-based management, we also wanted to implement a full application. So basically, this is our tool. So we implemented Faber's Multi Information Accelerator. So Faber is a hand-optimized HLS-based framework that basically creates image processing pipelines. And what it's good for is that it uses a lot of parameterization to allow you to create very parameterizable pipelines that depend on sort of metric you want to compute and also the amount of parameterization that you want for the given use case. You can see here that the Multi Information Accelerator is the dataflow accelerator with multiple stages, where we take a float image or reference image, and we compute the joint histogram of both. We sum the joint histogram, and then we compute the entropies for the marginal distribution and also for the complete sum histogram. And from this entropy, we compute what's called the mutual information method. So we have some preliminary results on Faber, which show that we were able to implement very similar accelerator with very similar latency. There are a few differences that are, again, driven by some different sort of optimization that we do as opposed to how the code is originally written. But the main takeaway from this is that Faber is a framework that uses both C++ and optimized C++ functions, a Python framework to generate the parameterization for the accelerator, and also a make-file-based build system to basically generate the correct C++ code from the Python parameter-based parameterization to actually implement the accelerator. Whereas our framework with multi-staging allows you to have a single C++ program where all of this can be done, and you don't need to have other sort of outside parameterization, writing the code via script in a one-safe way, which is less important. So if you notice the results of conserved sources, it's apparent that one thing that March is not able to do as well is they have fewer parameterization. And this is because one part of the automation framework Faber, what it does, it basically computes the minimal bit width for histogram computation, and it just uses these values. Whereas at the moment, March is standard with 32-bit values. So we are working on actually implementing this because it's very possible to do in our framework. And it's also a good showcase of what we can do with staging because basically you can compute at runtime what is the actual bit width that you want. And once you have completed this, you can set it to in your first stage and then produce optimized code afterwards. So this was all from my side for now. Thank you for your attention. And if there are any questions, please ask.
Thank you, Francesco, for your talk. I was wondering whether, well, you mentioned some future optimization that can be performed. So I was wondering whether you have in mind also some different kinds of optimization that can be performed with the multi-staging approach.
Okay, yeah, thank you, Laura, for the question. So similarly to the way in which here we are looking at basically optimizing bit width for a histogram, there is also a set of optimization that look at basically transforming floating point computation into fixed point computation. And also in those cases, what you need to do is you need to do a dataflow analysis on the program to understand what are the pessimistic ranges for the fixed point implementation that you can afford without losing too much precision. So this is, if you think about this, sort of a similar problem to the bit width of the histogram, but it's slightly more complex because depending on the type of computation you do, it will change dynamically depending also on the input data. So the neat thing with multi-staging is that you could also perform this analysis at runtime, figure out the correct bit width for the fixed point implementation, and produce optimized code for the use case. So this is something that we are looking at and looking to implement.
Thank you for your answer. Thank you also for joining us, and see you to the next Friday talk.
Thank you.